Okay, guys, we're still doing charge distributions. Everything we've done so far has dealt with the linear charge distribution, but there are other types of funky charge objects that we might want to calculate the electric field for. So now we're just going to more quickly go through those other scenarios, or at least the general equations for those other scenarios. Okay, so here's another scenario. You have instead of having a one-dimensional line, you've got a two-dimensional sheet of charge, okay, and you still want to calculate the electric field at some point, maybe above, maybe below, maybe beside that sheet, okay. What are you going to do? You're going to do the same kind of thing. Now, instead of breaking up, like we broke up the line into a little line of charge, now you're going to break up this two-dimensional sheet into a little two-dimensional area, okay, and I'm going to call that dA. That's our little two-dimensional area, and you're going to figure out, okay, what the electric field is from that little two-dimensional area. Okay, this is our separation vector. You're not just going to do for this one little two-dimensional area. Of course, you're going to use an integral to figure out what the cumulative electric field is from all of the charge that's spread out on this sheet, okay? And again, it's just like what you guys have always learned about calculus. You can imagine breaking this up into a bunch of little sheets, calculating what the field is from each of those sheets, and then summing it together. But we're not going to do a sum. We're going to do an integral. All right, so our next general case is a sheet, okay, with a continuous charge distribution. I can't spell right now. I'm running out of room. I'll put it down here. Okay, again, continuous just means that it's something that can be described by an equation. So it doesn't have to be a uniform charge distribution. Okay, again, maybe there's more charge on the outside and there's less charge on the inside, and you can describe that with some kind of formula. That's fine. Okay, and this is, of course, useful for charge sheets. Okay, maybe disks. Okay, hollow 3D objects really are just sheets of charge that are bent into some shape. Okay, so let's say we know something about the charge per unit area. So if the charge per unit area is known to be sigma, then I have the same kind of relationship I had before. Sigma is really just the little bit of charge on a little bit of area, okay? And that means that my charge here is equal to sigma times a little bit of area, and I can use that now to write out what my equation for the electric field would be. We'll start with the general case that we had. So that was 1 over 4 pi epsilon naught, and then we had the integral of 1 over our separation vector squared, our r hat, script r hat, and then this was dq. But really, every time we take this, we're going to replace this dq with something that's more useful for our shape. So in this case, for the sheet, we're going to take this, and now our electric field is going to be equal to 1 over 4 pi epsilon naught. Okay. This sigma, like I said, it could be some equation that tells you how the charge is distributed throughout the sheet if it's not uniform. This is still going to be there, okay? This is the same. The difference is now, right? We've taken this bit and we've replaced it with this here, Okay, and again, we've got, let me miss the vector sign here. We've got two different types of position vectors. We've got the regular one, and then we've got the primed example. And I'll draw a little coordinate system here just to remind you of why that is, right? This is going to be our prime because, right, this potential formula is telling you how the charge is spread out throughout the sheet. That depends on the location of the sheet, not the location of where you're calculating the electric field. And then the other R, that other position vector just points to the actual point where you're calculating the field, which is what comes in right here. Okay. And then again, this guy is here. That's the magnitude of this vector. And then this is a unit vector that is in that same direction, but has a magnitude of 1. Okay, so that's for our sheet of charge. Let's do another possible example. Okay, another one is, imagine this is now a 3D object. Okay, and I can now take a bit of this 3D object, right? I'm still trying to figure out the charge at some point up here, some point P, okay? But now I've got a three-dimensional volume of an object, and now instead I'm going to break up my little volume, okay, into little pieces of volume, so itty-bitty bits of volume. I'm going to call that d tau, okay? This is an itty bitty volume. Okay, and so now we're dealing with a volume with a continuous charge distribution. Now the charge per volume, we're going to use the symbol rho for that, where again, just like before, rho is going to be equal to dq over d tau, our little bit of volume. So now I can rewrite dq is equal to rho times d tau. Okay, and hopefully this makes sense now. I've got our electric field equation, our integral is now going to be 1 over 4 pi epsilon naught, okay? But now I'm going to have rho. This is going to be r prime, again, because it's going to depend on the position of that piece of volume of whatever that object is, okay? That's still going to be the position or the magnitude of the position integral squared. That's still going to be our unit vector. And now this is going to be a taken over a volume. Okay, so I'm being a little lazy here with my integral signs. Hopefully you guys can figure out this is going to be a volume integral and this is going to be an area integral. So really this, I need to take this over two limits, which describes how I can actually integrate over an area, a two-dimensional object. This volume integral really needs to have 3 integration limits, which will allow me to integrate over a 3-dimensional volume. Okay, so we're going to get some practice with that, but it's really not that much harder than doing a line integral. You just have to, again, be careful about how you set it up.